So one of the things that people usually struggle with when being introduced with recursion is being able to take a problem and actually write it in terms of a recursive method. Okay, it's not always apparent when you're starting out, right? Essentially, what we want to do is we want to practice writing recursive methods, so in the future, right, we can actually have it kind of as in our toolbox, right, of ways we can solve problems. But first, we need to get used to it. Now, because people have issues with that sometimes, what I'm going to introduce is something not in the textbook. This is something called the Fantastic Four approach. It's a way to analyze recursive methods or recursive problems, right, and try to figure out how you should program their solution. This particular technique is coming from a book called Introduction to Programming Languages, which is by Chen and Tsai. Hopefully I'm pronouncing that right. So this is outside of our textbook. If you look in Blackboard, there should also be kind of an additional handout that has a little bit of information on it. But we'll go through it here just as a way, right, or a scaffold, right, for you to understand, how to go through a problem and structure it recursively. So for Fantastic Four, there's 4 steps, as you might have gotten from the name. So if we do these 4 things, we'll essentially have done all the work we need to do in order to write a recursive method, right, or a recursive algorithm. So first thing we need to do, formulate the size n problem, right? So our first step is to identify what that full problem is. Second thing, and we're gonna go into these in more depth, right, over the next few slides and do a couple of examples. Second thing, right, identify the base case, right? Where do I stop? When I stop, what is the return value that corresponds with that? Right, so I'm getting kind of the ends of it, right? I'm getting the beginning, I'm getting the end, right, of this recursive process. 3, formulate the size m problem and find m. So m is the term that we're actually going to be using now for the subproblem, right, for n minus 1, right? Rather than having to say n minus 1 all the time, we'll just say, oh, it's the size m problem, right? It's the subproblem. So got to figure out what is that thing exactly. The last step, right, once we know what the full size problem is, what the subproblem is, what we want to do is figure out some way to construct the solution for the size n problem from the size m problem, right? How do I build the full size problem from the inner problem? So these are the 4 steps. We're going to go through these and then see how we kind of apply these to a couple of problems. So what we're going to do is start by going through these 4 steps in terms of factorial. So if you're doing something like a mathematical function, typically the size n problem is simply the problem you start with, right? Find factorial of n, right? That's the whole problem, right? Factorial of n, right? Or sum of n, right? That's the whole problem. In general, right, that n value, it's representing a couple of things. The first thing it's representing is some parameter to your problem, right? The numbers you're working with. The second thing it typically indicates is the number of repetitions, right? The number of iterations, the number of recursive calls, right? I need to do n different things in order to solve it, right? If every time my subproblem is one smaller, well, then I'm gonna have to do work n number of times, right? As I make the thing smaller and smaller and smaller until I get down to the base case. So a lot of times n is the number of calls that also needs to be made. So it has 2 meanings there, right? One is very specific to your code. The other is, oh yeah, it's simply the size of my problem, right? I'm trying to find factorial of n. So what we'll do here to kind of maybe make our life easier is we'll say, okay, the size n problem is literally going to be the function int factorial int n, right? So we're going to say this is the full thing, right? I want to compute factorial of n, right? I mean, I could use math notation here, but think in terms of a method. So int factorial of n. If you want to describe this verbally, you might also say something like, factorial of n, right? The whole thing. The whole thing is, of course, the actual problem we're trying to solve. Now that we know what the entire problem looks like, we want to start thinking about what is the base case and what is the return value. So base case, right, is where we stop. And then when we stop, what is it that I should return from it? Remember that we want to make sure that our recursive methods, right, our recursive algorithms always terminate, right? So what is that point there at the end? We're going to need to think about that. Well, for factorial, it's relatively simple, right? We said, okay, factorial of 1, that was just going to be 1, right? So factorial of 1, so factorial of 1 equals 1, right? That's our base case, right? Our base case is n equal 1, right? That's our base case. And then our return value, right? That's going to be the 1 also. So that's sort of the second thing we want to think about, right? We thought about what is the largest problem. Now we think about what is the smallest problem, right? We need to identify those 2 kind of ends of the problem, right? That's our first 2 steps. So in general, right, if you think back to what we talked about earlier, what will happen, right, is that when we start to actually write this thing, and we'll do it in a couple of slides, is this whole base case and the return step, or the return value, right? This is going to end up being the first part of our method, right? We want to check this before we go down to the general case, right, to compute the factorial for the other values of n. So the next thing we need to think about is the subproblem, right, the size m problem. So the size m problem, right, this is our subproblem, right? This is our problem that's slightly smaller than the full size problem, but yet is still the same type of problem, right? So it's just a little bit smaller. In terms of factorial, that's the n minus 1 factorial, right? That's still a factorial that I need to compute, right? But it's a slightly smaller one than just n factorial, right? Slightly smaller than the entire thing, where I need to find a little bit simpler to find factorial is what I need to compute. For something like factorial or something like sum, that subproblem, right, is typically just n minus 1, right? Our size m problem is simply n minus 1, right? Because our problem got simpler by 1. But that's kind of very specific to mathematical functions, right? In terms of other things, it's not exactly going to be as, n minus 1, right? Real problems are much more complicated than that. For those, right, of you who have already looked at the homework most likely, depending on kind of what semester you're watching this video, the homework is maze generation. And so you're actually asked to create a recursive algorithm to randomly create or randomly generate a maze. And that actually involves dividing a maze into 4 parts. So rather than kind of the subproblem being n minus 1, the subproblem is more like n divided by 4, right? There's 4 mazes inside of every full-size maze. So this can look a little bit different, right? The n minus 1 is very much specific to the fact that we're doing these kind of easy examples where factorial or sum, right, you're getting smaller by 1 each time. So at this point, we figured out this bit here, factorial of n minus 1. This is my smaller problem. So I have factorial of n minus 1, and this is where a little bit of magic happens. What I'm going to do between this slide and the next slide, or this step and the next step, is assume that I can compute this, right? So even though I haven't written a factorial function yet, I'm going to assume that if I want to compute the answer to the size n problem, I am free to use the call that solves the size m problem, the subproblem, right? So even though I haven't defined it yet, it's kind of circular in nature, I'm just going to go ahead and assume that I could compute this little bit if I wanted to. So let's say I have that. What do? My next step is to think about how I can compute the whole thing, right? The size n problem. Well, in that case, I can use the size m notation, right? I said that I would assume that the size m problem can be solved. Well, in that case, right, I know that I have this available to me, and then I can just say, well, the full size problem is me doing doing this, right? N times factorial of n minus 1, right? So I assume that this exists, and if I know that I can compute the factorial of n minus 1, I know it's simple to get the factorial of n, because I can write n equals, or factorial of n equals n times factorial of n minus 1, right? I already have this assumption that this part works, right? This is assumed to work. I don't have it yet, but I assume it is. And if I assume it does exist, then I can easily define factorial by saying, factorial of n is n times factorial of n minus 1. So I'm using something before I've defined it. And as I do that, right, as I write that line that says this is what should happen, in that kind of moment, I am actually defining factorial, right? So I'm using factorial at the same time that I define it, and that's kind of the magic of recursion, right? I assume something that exists, then I use it to define itself. So I don't actually need to know, every step of how to define or how to solve factorial. All I need to do is know how to do a little bit of work, right? That n times, and then I assume that the second part, right, the recursive call, this stuff over here, will work out, right? So I'm assuming that happens. If I do that, it'll actually work with me not actually explicitly defining, how exactly do I get to size m. It'll just happen automatically because it's a recursive algorithm. So at this point in time, maybe you can go back and look at the slides, but we've kind of discovered these different parts, right? We've discovered our full-size problem was factorial of n. We figured out that our base case was 1, right, and then it returns 1. We figured out how to compute, right, our full problem from the subproblem, and all that's really left at this point is to write up an actual method that computes factorial. I'm not going to write this out in the slides here. What I would suggest is you go and try actually putting these little pieces together, right? You can try putting those pieces together over in your favorite IDE and see that basically, right, we've done all the heavy lifting here, right? Which is just kind of ends up being a bunch of different fragments of code for you to paste together, right? And that'll give you your recursive method. So what I want to do, though, is kind of switch to a different example. And what we're going to look at now is how to apply this when we have the problem of printing out a list. So this is kind of a basic form that says, okay, these are the 4 things I need to do, right? So this is in your head, right? Imagine you're trying to apply these steps to the problem you're working on. Let's say, right, we want to print a list. So 4 things to worry about. So first thing here, and actually, I'm going to go through these, right? I'm going to tell you the answers to them, and they're also on the next slide. But really what you should do is maybe pause this for a second, try to think about these a little bit, or you can do it, one at a time as we go through them. But make an effort to see if you can figure these out on your own before we talk through them. All right, so let's try applying Fantastic Four to the problem of printing a list, right? So this is completely different than the mathematical functions we've talked about before, and it's actually related to kind of the recursive definition of a list that we talked about a while ago. All right, so printing out a list. First thing we need to do is formulate the size n problem. Well, size n problem is the full size problem. So for this first part here, I might just say something like, it's printing out the entire list, right? So it's list print of head, right? It's list print of the first node, and then after that first node is everything else, right? The rest of that list. So printing out the entire thing would be my first thing there. So that's my size n. The second thing, right? Find base case and the corresponding return value. Well, what I can do here is I can ask myself, what is the simplest possible list I could display? An empty list. So that's actually something I could choose here for my base case, right? My base case could be when I get a null list, right? When there's nothing in there. Here I'm printing out, so I don't really need to worry about a return value, right? I'm probably going to end up having a void return type. So I don't really need to worry about that right-hand side. All I need to do is remember that, hey, my base case, right? My base case is for an empty list, right? That's the trivial thing to print, right? To print out an empty list. So we got some ideas there. So number 3, formulate the size m problem and find m. Well, the size m problem is doing a print list on the node, the head, dot get next, right? So not just printing out the whole list, but printing out all the nodes after the first one, right? That's my subproblem, right? I'm going to do a little bit of work to print out the first problem, and then recursively I'm going to say, okay, I need to print out the rest of this list. So that'll be my size m problem, right? It's printing out the tail of the list, right? Everything after the head. So the last one here, number 4, right, is how do I construct the solution of the full size problem, right, the size n problem, from the size m problem, right, the subproblem? Well, that turns out to be relatively simple. We print the head of the list, and then we call ourselves recursively on everything that's after that, right? We go for that. We go and we try to solve the subproblem, right? We do a little bit of work for the first node in that list we're displaying, and then we recursively go and display the rest of the list. So that's how we would construct the solution to the entire problem. So let me go forward here, and this is the slide, right, that has kind of the answers here. So you can see here, right, display of kind of the whole thing, right? You can picture this, right? This is maybe head, right? If you want to be really specific, this is the head of a list, right? And then, right, our stopping addition, right, is, or our base case, right, is when we have node equal to null, right? There's no list, and we can finish up. And then over here, right, for display, right, subproblem is, do a display on the tail of it, right? Everything that goes after the first node. And then to solve the entire problem, right, really what we need to do is print out one node and then do that step we talked about a second ago that prints out the rest of the list. So this is our basic kind of implementation of so this is our basic analysis of how we print a list recursively. So what I'm going to do now is jump to an IDE and show you guys kind of the finishing touches here. So keep this in mind. Let's go ahead and code it. So let's take a look over here. So we said, okay, formulate the size n problem. This is what my method is going to look like. So I'm actually just going to copy this code here, go down here, paste it in. Now, I guess I should note here, this is making the kind of the analysis method seem really simple. Keep in mind that it's not always going to be this simple, but this is just kind of our first kind of full example from this, so since we need some place to start. Okay, I'm gonna again do a copy paste. Like I said, it's gonna be more complicated when you have a real problem, but we'll start with this. All right, so display list is gonna be a recursive method. First thing I need to do, right, is check my base case, right? I want to make sure that I can actually finish something, right? I want to stop at some point. So over here, right, I've already figured out what the stopping condition is going to be, and so if I have that, I can go ahead and return from the method. So I have that, so I know now this thing is going to stop if I run it. And then what I need to do, right, is I need to print out the current node, right, and then display the rest of it, right? I need to do a little bit of work, right, a little bit of work to make my problem simpler, and then I need to call myself again on the subproblem. So in here, right, what I'm going to end up doing is I'm going to do system out.println of node.getElement, right? So I'm doing a little bit of work to print out this first node. And then after that, right, I can go and I can call myself recursively. And this is the same code up here. I'm just typing it here just because. So display list of node.getNext. So this is our recursive implementation, right? So in this case, right, this looks a lot like the Fantastic Four analysis we did earlier. Now let's go ahead and try running this. So I'm going to take this off. I'm going to try print list instead. Or actually, let's go display list to use the proper name there. And we also need to make that public and static so that we can actually use it. And then let's run it. And over here we get 5 and 7. While we're at it, right, while we're kind of practicing our code, let's go ahead and jump into the debugger for a second just to see how this thing works. I'm going to set a breakpoint here on line 20. So this is going to pause my program, right? So once I've set up my little mini list, right, I'm going to go over here and kind of watch what goes on as I run this thing. All right, so I've set up my list. I'm going to go and call my recursive method. So initially, right, head is of the linear node that contains the number 5, right? It's the first node in my list. So let's go ahead and go inside that method and see what's going on exactly. So jumping over here, I'm still looking at that first node, right? The node that contains the number 5. And then I do the check, right? I compare that node with null. Well, initially that node is not null, right? It's actually something to look at, so that ends up being false, right? And I kind of move along, right? I don't need to do anything else. The next thing I do, right, since I didn't have to return there, right, since I have some work to do, right, I didn't hit my base case, is that I need to print out something, right? So I need to print out that first value, right, the first node in that list. So I'll go and do that. And over here, right, you can see, right, the green, right, is indicating the line I'm currently on, right? I just executed line 27, and the next one to execute is 28. But down here, right, you can see that first thing, that first call, right, it's printing out the number 5, right? So that println got the first node. The next thing that happens, right, is that I do have my recursive call. So my recursive call, right, it's calling the same function again, or that same method again. And then here this time we're doing node.getNext. So let's go ahead and try that. Over here you'll notice that we are inside the method again. And over here, because we did that, kind of that parameter was set as node.getNext, the parameter being passed in now is 7, right? So it's that second node, right? We've advanced forward by 1. So now node is 7. Again, we check to see if it's null. It's not, so we skip forward and keep on going. Then we do the println, right? So we print out that particular node. So print that node, get its element, display that 7. Now we're at the last line, and we need to do the recursion again. So this time, if we look at node, we see that it's equal to null, right? Remember that we created a list of 2 elements, and then at the end, right, there's always going to be a null there that says, oh, this is where you stop. So at this point, right, we've done a dot next twice, right? Dot get next twice, so we're at the end. So in this case, right, node equal null, well, that's it, right? You have to return. So returns from the call that printed out the last thing, returns from the call that printed out the thing before, and ends up back at the main, right? Ends up back at line 21, and the program completes. So you can see kind of the trace, right, is that we recursively called it, and we worked our way through the list, and we updated node each time, right? This line here, right, is working similar to this line over here. This line over here, right, is working similar to this line over here. This may not be a really good example of recursion simply because this isn't super simple compared to this. But hopefully it's something that lets you see kind of a general uses of recursion, right? Rather than just looking at mathematical functions. Because really that's what we want to do, right? Is we don't want to just write solutions to problems that are, defined on a piece of paper as a mathematical function, but we want to do real things, right? So a list is kind of a more reasonable thing to look at in terms of how recursion can be used. Simply because lists are recursive data structures, so it makes sense that we might consider using a recursive algorithm or recursive method to do stuff